So I'm very happy to be here today. I will discuss recent work in which we show the high dimensional limit of stochastic mutation algorithm. But before I dive into the details of that work specifically, I wanted to give you a broad introduction to my field and my research. So classic. Okay, so my research is in the interface between statistical physics and high dimensional probability and communication and machine learning. And the idea that we want to use a measure from statistical physics and high dimensional probability to understand many questions in machine learning. And the relevant question, as you all know, and I don't need to introduce many of them, but about the training dynamic, generalization, architecture design, why we actually modern machine learning algorithms do not overfit, and many more. But maybe one slide in a nutshell, what do I mean by statistical physics? So statistical physics usually it means to kind of analyze microscopic systems of interacting entities, that it's particles, molecules, neurons, and parameters in the context of neural networks, for example. And the idea is that usually you don't have access to these type of interactions, and it's usually very complex system and random. And so what you want to what people usually do is they think about it in terms of ensembles when they constrain certain quantities. For example, that could be energies of particles or number of particles. And what you do have is measurements. So you look at microscopic behavior of nature, at observables. And usually that's the hardest part to find. What are the good observables to look at? And what we would like to have is some kind of identify some physical or universal phenomena that we see across many systems. So in this kind of mindset, we think about complex and random systems from statistical physics as well as complex and sheets. And in that sense, it's kind of natural to think about large different size. And what I will focus today is a little bit different than the usual, than the classical learning theory, that I will think about typical behavior, and I will take a concrete model for my data that will be a little bit different. And the idea is to search for some certain symmetries and degrees of freedom that help me understand the behavior of my system. And then other things that people have been looking at today in the context of neural networks and machine learning is kind of scaling law and universal phenomena. And I will say that there is deep connections to high dimensional statistics and Bayesian instruments and information theory. So they are all connected, and sometimes it's just a matter of different terminology. And in terms of, with highlights kind of things that I will not have time to discuss a lot. But one of the topics that I'm very much interested by is in the context of neural network, going beyond this infinite with result for these neural networks. So what is known is that if you look at neural network at the infinite with limits at initialization and initialize your weights such that the variance is 1 over the length of the number of neurons in the layer, then what was shown is that the network kind of the statistical is kind of simplified and can be described by the Gaussian process. And so what we can show is that we are able to go beyond this type of result that kind of doesn't take into account the learning process of the data and provide another Gaussian process that is kind of for finance with the neural network. And this type of idea allows us to provide analytical prediction of the network outputs and compressed representation of the network. And we also use the kind of diagnostic tool. So this type of approach also allowed us to identify phase conditions that we see that are kind of similar to a lot of systems in physics. For example, the condition between vapor and water. And we can use it for different data structure and use it also to understand something about the learning. And in terms of in another branch of what I do is connected to generalization and information. That's also something that I'm interested in. It's also very connected to this point of view of neural network. It's from this Bayesian point of view. But what I'm going to talk today mainly is about the optimization part, which I call it the non-equilibrium part compared to the Bayesian part that I think about it as the equilibrium part. And I will introduce this framework for stochastic optimization. So let's start with that. So just to say that this is a joint work with this before Elliott from McGill University. And so what the main question that we will ask is about how do the learning process look like, and we will have an exact formula for the dynamics of SGD, the generalization dynamics. And in particular, what we will add in addition is the effect of the data structure on the dynamics. So in general, what do I mean by optimization in high dimension? So in any typical problem, what you will have a set of samples that are drawn from some unknown distribution. And what you want to do is to minimize a set of parameters with respect to empirical disk. And typically your end goal will be to kind of, even if you don't know the distribution, but what you would have liked is actually to do the average with respect to this distribution. So that's kind of like one of the main challenges of machine learning. But on top of that, when we think about high dimension, then the issue is that both the number of samples that you have is very large, but also the number of parameters is very large. And this is kind of motivated by what happened today with state-of-the-art algorithm, which contains billions and sometimes trillions of parameters. And it's kind of natural to assume that the number of samples is roughly of the order of the number of parameters. So a little bit about the optimization process. So usually, I guess most of you are familiar with that, but the easiest way to do it is gradient descent. But actually, because we are in high dimension, this is not very realistic. So what you typically do is stochastic gradient descent. And I will focus on a particular version of the stochastic gradient descent in which you, at each iteration, you sample new examples, and it's a fresh example that you haven't seen before. And what is important is that my learning rate is fixed. And such that at the end of the day, you essentially estimate the full equilibrium. And in addition, what we will work with is this in this limit in which the number of samples and the number of parameters is roughly at the same order. So meaning that I'm thinking about the number of iterations that are of the order of the number of parameters that are. So a little bit about the history of the problem, and I guess there is also expert here much more than me. But stochastic gradient descent in finite dimension, then one can show that if you take the number of samples to be very large and you consider very small step size, then you have a low Flash number and you converge to gradient flow. So that's already known, already from the 50s. But what happened in high dimension? So in high dimension, the issue is that essentially you cannot really take the number of the learning rate to zero, because then it would take you a long time to train. And so it's natural to take this fixed step size, and the question is, what is the limiting equation if that fits? So I cannot really answer this question for general distribution of my data. So what I will focus on is on a particular set of distribution, and this type of idea is usually called the teacher-student model but I guess there are many names for this, but the idea is that I'm thinking about the way I generate the data. So as you are a teacher, and you're generating input and output yi. And so the way I'm generating that is that I'm taking a function phi that is general and a set of parameters x star that has some low latent dimension of star, which is smaller than the input dimension d, such that I'm doing this low dimensional projection of my input on this x star, and taking this function and adding some noise in the way I left. Okay, so this is yes.
So what will be phi, and is it the same functional class as the one we studied?
So for now, phi is general. After that we will focus on particular examples, and we will show that. Please ask me questions if you haven't heard it.
What you're trying to do is take a fixed size, right? I just want to
Yes.
make sure I understood.
Yes.
So you're taking a fixed size and taking D and roughly the same way to infinity.
Yes.
And you would like to characterize the dynamics of the GD. What's the?
Yes, I want to characterize, and I will give an exact equation for the dynamics of the GD in this region.
Like the thing analogous to Gardner Fellow.
Yes. Yes, exactly. Yes.
So that notation of the noise being inside, meaning you implicitly assume you apply the noise before applying the function field deterministic. So logistic regression would not be covered.
No, it's logistic regression is covered by this. Yes. So
isn't epsilon infinite on the logic scale before you apply the inverse logic transformation?
For the logistic regression specifically, we consider the case in which you don't have the noise, but you could add the noise.
No, it's implicit. The noise is implicit.
Yeah.
Because the data is not a deterministic function of the probability.
Yes.
Okay.
The main point is that that the noise and the data and the AI are the randomness part that you have, and X star is kind of for me the deterministic.
My only question is, are you going to use the fact that you add finite variance noise and then do deterministic transformation? In which case, I don't think logistic regression will start.
There's nothing additive in the expression, right?
It doesn't have to be additive, but finite, if you want it to be finite variance before you apply the deterministic transformation. Right? The logic is plus minus infinity for to get 0, 1 after a deterministic transformation. I think. Okay.
We can discuss about it afterward. I don't think it's a problem, but we can discuss about it. I will soon know that my AI are generated from Gaussian is a Gaussian random variable, but has a general covariance matrix, and that allows me to enter structure in the data. And though this looks restrictive, it's actually covered quite a lot of examples. Okay, so that's how the data is generated, and in that it also includes, for example, a two-layer neural network in which L star would be the number of neurons in my in the neural network, the data. And now, so the data, so now that the teacher generates this data, you give it to the student. And the student has a task that he wants to find the best mapping between AI and YI. And so he kind of had the hunch that the teacher did this high dimensional projection. So he does the same, but with some other latent dimension L because he doesn't know what is L star, and he doesn't know what is X star, and he doesn't know also the function phi, so he chooses a different function. And the nice part about this problem is that, and now I'm thinking about, essentially when I think about the population risk, I want to kind of take the average over the distance between the function of the student and the function of the teacher. And in the end of the day, everything is just a function of the low dimensional projection of the teacher and the student and the noise. So the randomness is driven by by the noise and the teacher.
So how come G does not appear on the right?
It's implicitly appeared inside, like inside there. I called everything F, but it's implicitly appeared inside. I mean, that depends. It's just that when I'm thinking about the randomness part, then but maybe it's also connected to your questions. Okay, so let's start with a simple case when there is no structure in my data. So I'm thinking about AI that are generated just by isotropic data. So what we can say is that because I can just track the norm of my iterate and the overlap, essentially the inner product between the teacher parameters and the student parameters. And what we can show is that if you look at these two processes, they converge with overwhelming probability to a continuous process that is deterministic. And the idea is that we scale the time a little bit different. So we think about one iteration of SGD as T times D iteration in the new process. And the idea is that we take D to infinity, and that's what caused the process to be continuous. And this B satisfies an explicit equation that we can write. And essentially, you have the first part that is the gradient term, and the second part that is the noise term, and it is explicit, and it really depends on the gradient of the noise, and you can interpret it as a Fisher matrix. But it turned out that this type of equation was posed without proof in the statistical physics literature for the case of square laws in 95. So already then they have thought about this type of ideas. But they were interested by two-layer neural network. And since then, there was a lot of interest in this work, both by mathematicians, physicists, computer scientists, considering several problems, Basel table, tensor PCA, also the GLMs, and again, two-layer neural networks.
So when you say without proof, you mean as a conjecture or as physicists do?
As physicists do. I'm allowed to say that because sometimes I do that too. So, but yeah, so they essentially the difference now, to be more precise, is that when you take concentrating objects, you don't calculate the error. You just say that they concentrate and you replace them by the mean, for example. That's kind of, and you don't measure the error how close is this process to the two one. Essentially, you compare the simulations. And so for the structural case, there was not that much work. There was a work with my collaborators in which they studied the linear case, and they did it for multiplus, but they used a lot the linearity of the problem. And there is another work by physicists in which again they managed to write to the equation, but they again without any proof, and again just for the square laws case. And so, what is so hard about this structural data case? So the problem is that I cannot really write this autonomous set of equations the way I did it for the non-structural case. And the reason is that you have kind of proliferation of terms. So you will have terms that will appear as kx, kx squared, and so on. And so the way we found a way around it is to use some kind of an allometric theory tree, essentially to use the resolvent. And why the resolvent? Because if you take the resolvent and you multiply it by the metric itself, then you get the resolvent. And essentially you can expand the resolvent to any polynomials. And essentially you can write now any polynomial function by just doing contour integration, encompassing all the eigenvalues of the matrix space. So I can simply write any polynomial function. So how can I use this? So the idea is that the way I tracked before the norm and the overlap, now I can simply track a slightly modified norm, which is the norm that I insert inside the resolvers. And the same thing also for the overlap. And the idea is that now I can, using this, I can do it the same and write an autonomous equation for these two objects and show that indeed you have the same convergence to a deterministic limit. And again, everything is scaled, the time is scaled such that each time I'm doing complete iteration in this unit. So kind of the implication of this theorem is first that we can address general covariance structure, and I was also saying in the end, how is it useful also to study other stochastic optimization, for example, the cases of multipaths. But just in how do from the norm though and the overlap, I can get to study the loss function itself, which is in the end what I want. Essentially, I want to find the loss itself. So the idea is that because the loss function is an average over the low dimensional projection, and these are essentially Gaussian Lambda vectors that has the following covariance. And it has just one power of the matrix H. So in the end of the day, using my resolvent, I just need the linear function of Z such that I can write the resolvent. There was a question. So that allows me essentially to write also the equation for the loss function, and essentially I can also write any function that I. And I will show also how do I use this to construct the Leningrad threshold and analyze stability and optimality of the points. And maybe if you don't like this representation, so we have another way of. Yeah, question.
Just a quick question.
Yeah.
Can you give us an intuition about what the role does do like in homogeneous eigenvalue spectrum affect the learning? Just from
Yeah, I will show that in examples. I will show that in example. That's essentially our goal in the end to show how that affects in this. So we show that in example. It affects also the threshold on the. So it's also connected to the way we are proving the result is that we construct a continuous process, essentially a stochastic process, and that we compare to this SGD process. And the idea is that here you can really see how the fact that you sample each time one example at a time, what noise that generates. And so we can simply work with this process, and which again scaled in a way that one iteration of SGD is T times D in this process. And what we can show is a similar kind of log large number is that for class of function, like it's even infinite class of function, that comparing SGD over this function is almost the same as comparing this process on this separate function. So I'm not saying that they are essentially the same, but on an infinite class of function they are.
So I'm just a little bit not sure about the step size. So you're saying that gamma is fixed, but you're scaling gamma by 1 over D in the.
Yeah.
So where does the factor of 1 over D comes from? Because
So the factor of 1 over D already appeared at the iterate that I had before. And you're right that this is not the usual way, but in order to make all the terms to be finite, you need to this. It's kind of, it's crucial because of the way we are taking these to infinity, otherwise everything will just go to zero.
But in practice, we have very large dimension and not very large step sizes. So, well, where's the difference from, and it doesn't
I
diverge.
mean, it's, what do you mean? Doesn't say so?
Tiny step size, very large then.
Sorry?
The step size in practice is larger than it's given.
Yes.
Yeah, I think it's in a way, how do you scale your gradient? If I would not do that, then I would need to scale the norm of my iterate such that it would scale somehow with it. So it's a way to kind of scale the norm of my iterate that they will be afforded once.
So at least in the model that you write down, you're saying that we really need the scaling, otherwise SGD would not work well.
Yeah, I think it's just it's it's just a matter to keep the, so that in my equation everything would be order one, but I don't think it will change the.
The state that.
Yes.
According to the equation, will remain bounded.
Yes, that's.
So basically the gap is between your kind of model that you analyze and say neural networks in practice that have all kinds of normalizations that make this unnecessary.
Yes. Yeah, no,
And in fact, this equation, say noise term, but it's completely deterministic, right?
the part that is not deterministic is the Brownian function.
Also, it is stochastic.
It is stochastic equation, yes. Yes,
I see. So we're comparing here to stochastic processes.
exactly, yes. So the kind of, like, if I go back to the picture that I had before, with running flow, that, and then I would say that this is kind of a linear equation, though again, it's not exactly, it's over this set of functions that I'm considering. But this is a way to say that in high dimension, when you're considering fixed step size, then you have this additional noise that kind of is very important and it's not always helped you. So it can be bad.
Can you show again how do we compare the two stochastic processes? What's kind of the.
So you need to choose a class of function that you compare it on them, and then essentially you need to show that this map is kind of contracting and show that the marginal part is that's kind of the idea.
Or this happens with very high probability.
Yes. Yes. So maybe that was very theoretical, and there was like a lot of question about how does it really look in practice. So let's start with just a warm-up. Linear regression, which is the simplest case. So in this case, I'm thinking about my function phi as linear with additive noise, and G will be also linear. So in that case, I can really write everything explicitly. And now I'm writing my function t in terms of this resolvent node. And then I can write an explicit equation for the loss function, which is defined in terms of these two kernels that are essentially just function of the discrepancy of x0 from the initial point of x, then x star, and the spectral properties of my covariance. So this is already something that I can compute and without even needing to simulate run. But maybe to your question, with the logistic regression part. So we didn't consider it with the noise. So we essentially look at that the student probability is just essentially a softmax. And the same for the teacher. So the teacher has the same structure as the student, just with X star. And for the two cases, essentially there's a sigmoid. And we looked at the cross entropy part. And this is essentially, we can really write an explicit equation for the loss. And I can maybe, if you're interested, I can show later what is the exact equation. But But you can see that as the dimensionality grow, then the uncertainty in our theory become smaller and smaller, and the prediction become better. So and the other problem that I want to show is a phase label, which is kind of canonical in the sense that there is this hard phase that makes it interesting. So the idea here is that I'm getting modulo of my vector, the projection of it, and I want to recover the phase of x star. And I'm assuming that the student and the teacher has the same form. So the issue with this problem is that from where do you start, essentially? So if you start with the Gaussian vector, then the problem is that if you take the overlap with x0 and x star, then it goes like 1/d in high dimension. So if you increase the dimensionality, then this overlap will be very, very small. It will take you a long time to converge. So essentially, that can be characterized exactly, and it takes deal of the iteration. But if you start with some kind of warm start in which you do have some information on the direction of x star, then one can show that it will take the iteration. And the nice part is that that can also be shown from our equation if you track the overlap and the ratio of nodes. So, and we plot it kind of a vector flow as a function of the learning rate. So for very low learning rate, you see that it takes quite a while to generate this overlap. But once you did generate the overlap, then you immediately also generate it. And you can see that there is like some kind of like difference between very small learning rate that is corresponding to gradient flow, and larger learning rate that where the noise kind of affect you more, and it kind of helps you to converge.
You see it only here or also when the difference from the calculation?
Yeah, you can track, I mean, we have the equation, so we can really analyze the so this is a kind of like the simulation of the equation of our equation.
But it's still a kind of complex equation, right?
Yeah.
And even the
Yeah,
factorizing is different.
yeah, but you can still look at kind of stability regime of the equation. So because even with that, you can show that there is regime which yeah, but you're right that at some point you're right also too. But you can also see it from if you look at the loss function. So you can see that there is this first phase of descent, fast descent. And then you have the starting point in which you're stuck and you're searching to where you go out. And then at some point you're managing to escape, and the same thing for the overlap, and everything kind of depends also on the learning. And the last part I want to show is something related to stability and convergence, and that's in kind of initial study of what we're able to do. So it's kind of turned into a question about optimization. So what learning rate can ensure the descent at each iteration? So the difficulty is to categorize the descent is that it's hard to find it exactly because of the stochasticity of the gradients. And so what you typically do is you track the distance to optimality. And we have essentially by our theorem, we have a deterministic analog for this distance to optimality. So we kind of change the question to what learning rate will ensure that the distance to optimality will be a decreasing function. And we have an exact equation for this distance to optimality. And which depend on these two terms, that one of them is negative and the other one is positive, which is connected to the noise. And so that tells you exactly what will be the learning rate that will ensure that everything here will be negative. So that gives us some kind of like dynamical threshold on the learning rate. But this threshold is now depend on the average eigenvalue. And if you do have some convexity and smoothness assumption, then you can show that this threshold is actually constant and it does not depend on time. And essentially, but the important part is that the dependency on the average of eigenvalue instead of the largest one, which can kind of show that we can show convergence for a larger set of learning rates. And we, yes.
Didn't you explain within classical optimization, the macro is the ratio, right? Largest to smallest eigenvalue.
Yes, that's exactly related to convergence rate. That's you're talking about the convergence rate. Yeah, so in our situation, we show that the convergence rate is connected to the average condition number and not with the regular condition. No. For the same group. And using this idea, we can also study logistic regression again without the noise. Showing the local under some local form assumption. And maybe this is kind of like a more a picture that shows how the distance of the humanity changes as a function of the covariance matrix structure. So here we looked at the last iterate of the distance to optimality as a function of the learning rate. And we plotted it for a different covariance matrix structure. And here it's a way to generate a covariance matrix structure that has a power law component. And so what we see is that if we scale everything such that all of them will have the same average eigenvalue, then you can see that kind of as we predicted, the threshold appear as at 1 point, they all collapse at 1 point, in which you can see that you will not have descent anymore. But the convergence rate does depend on the minimal and maximal eigenvalue. Okay, so to kind of conclude, I presented the framework to study stochastic optimization in high dimension, and we have this exact characterization of SGD in high dimension for several non-complex problems. And we provide this optimality condition that depend on the average learning rate, average eigenvalue. And in the paper, we can also extend it to time-dependent learning rate and the polarization term. And by studying the equation, we can also reveal something about the implicit bias of SGD related to conversion to a low norm solution. And we have also examples to that in the paper. So in terms of like what type of things we can do with that next. So one other kind of very interesting direction would be extending it to, and this is something that we actually do now, is to extend it to adaptive step size. So what happened also if the learning rate is a random quantity. And we can show that in that case, you can also have a deterministic analog. And maybe another very interesting extension will be to the multipass SGD, in which you were allowed to use example more than once. And from the work in the linear case, we expect that we can do this extension. There are some kind of challenges, but it seems like it's possible because of this consideration of the generic covariance factor. And what I am very much interested in is how to connect it to ideas such as special conditions and scaling laws, which is something that we kind of saw some of it in the context of phase integral, which depends on the initial conditions. So how do the algorithm converge? So it will be interesting to consider more example of that sort. And kind of I think that it would be interesting to extend it to more understanding of what the effect of the structure of the data on the dynamics of the algorithm. And we have universality. So we studied for the Gaussian features, but then we extended to more than that. Our proof technique suggests that yes, but it should also be a question. And one thing that we also showed before is information theoretic bounds. So we have information theoretic bounds on the generalization level of any estimator. So it will be interesting to compare it to SGD. but and also in the context of what I was showing you in the beginning, which is this idea of analysis of Bayesian neural network, as kind of this, which allows us to extend it to a multi-layer case. So it will be interesting to extend this analysis to a multi-layer case. We know now how to go from here to here by looking at some kind of thermodynamics bounds, but the other direction is kind of not so clear. And again, how do you put in both cases the effect of the structure of the data? And the study generalization, because here I was able to kind of look at the generalization dynamics, but in the context of the multi-layer case, it's a much harder thing. And with that today, thank you very much for the attention.